Hello students, welcome back. Now we are going to talk about a new category of sequential circuits, and these circuits are called counters. So in this video we are going to talk about that what is a counter, how much can we count if we have a counter with us. We are going to talk about two types of counters, synchronous and asynchronous, and other varieties as well. So let us get started. So first of all, what is a counter? Counters are used to count any operations or event that are occurring in our digital system. Counters are used to store these values, and we can fetch out the value and display that number which is already stored. This will tell us that this process has been repeated these many times, or we have counted up to this number x. Depending on which kind of clock pulse we are using, we have two categories. One is called synchronous and the other one is called asynchronous. Mostly the counters are designed using JK flip-flop. What is the reason? We will check it when we look at the circuit diagrams. So first of all, let us talk about asynchronous. Asynchronous means synchronization is not there. These are also known as ripple counters. As the name suggests, they are not synchronized by one single clock. Every flip-flop will require some clock, but they are not synchronized by one single clock. Different flip-flop will need a clock, and that can be a completely different clock. And for this specific reason, because of asynchronous behavior, sometimes we can get wrong output also, or the delayed output. The counting process can be slowed down. But there is an advantage. They are very easy to design. Now let us have a look at the block diagram. So here we are having 4 JK flip-flops. J and K in every flip-flop is given as 1 1. And if we recall our learning, we had learned that whenever JK combination is 1 1, the output of the flip-flop will be toggled. So when this J and K is 1 1, then this output is going to flip. That means at every clock, this output will flip from 0 to 1, to 0 to 1, to 0 to 1. Now do you see something interesting happening? This is LSB of any binary code that we generate. Now one more interesting thing that is happening, that this signal is going as clock to this flip-flop. That means 0 1 0. So whenever this 1 comes, we are getting a rising edge here. So after every 2 clock cycles, we are getting one trigger here as well. So this will also flip 0 1 0 1. Same way this one, same way this one. But whenever we traverse from one flip-flop to another, the operation speed will go down by 2 times, because now these 2 clocks will decide one single trigger. Then the next 2 clocks will decide one single trigger. So what is going to happen? The output of this bit will be 0 1 0 1 0 1 0 1, and this way it will keep on going. For these two, the output of the first one here will remain 0. For these two, it will remain 1, then 0, then 1. This is also toggling, but at half the speed. Then again half the speed. It is also toggling 0 1 0 1, but half of it, and then next. And we can see that we are generating all the numbers. This is how an asynchronous counter works. Now let us check the second type of counters. So here we have the second type of counters, and these are called synchronous counters. In these, all the flip-flops are triggered with one single clock. That means we have the synchronization. All the flip-flops are synchronized. All of them will operate at one given positive edge. The speed is going to be uniform and slightly faster also. The chances of wrong count will be minimized. We will get minimum errors. But the design is slightly challenging. We will have to wire a few more components along with the flip-flops. But in the previous design we had seen that only flip-flops were enough. Now this is the circuit diagram for a synchronous counter. As we can observe that every flip-flop is having a clock signal, and that is common. Every flip-flop is having JK as 1 1, so they are going to toggle. But this is not the complete diagram. I have just shown you the block arrangement, because if I consider this as my counter, then this counter is going to give me 0 0 0 0 1 1 1 1. That's all. Again it will give me 0 0 0. To make it count from 4 zeros till 4 1, that means from 0 to 15, I need to arrange some gates which will decide that when this trigger should come. Some AND gates, some OR gates. For that I need to solve a truth table, but I have not shown them here just to simplify the complete block diagram. So the design is little challenging, but it will be more accurate. Now we have few more different types of counter. The regular counters that we have, they will count decimal numbers like 0 to 9 and so on. We have n-bit counters. So here is the question. If I have a 4-bit counter, how many numbers we can count? Using 4 bits, I can generate 16 different numbers. That is 0, 1, 2, 3 and till 2 raised to power n minus 1. N is 4, so it will be 15. So 0 to 15. If I have 8-bit counter, we can generate 256 number, 0 to 255. We have decade counters which can count only till 9. Then we have Johnson counter which is going to generate some special patterns. We have more patterns that can be generated by very specific counters which can be designed using finite state machines. And we can also design the counters to count in the downward direction. That means not going from 0 to 9 but coming from 9 to 0. So this way also the counters can be designed. So it is all up to the designer that how do they count the events. They can count by skipping some numbers also. Everything is possible. We just need to have the specification, solve the truth table, design the finite state machine, and our counter will be ready. So students, now we know about the types of counter. Let us start designing some of them. The first one that we will design is a 4-bit counter. We'll do that in our next video. Keep learning. Thank you.